I do want to talk to you just a bunch of differentiation rules. At this point, we should have a general idea that a derivative is a rule. It creates for you functions that give you slope for various points. I want to start it off with something that looks like this. Okay, let's draw a graph. And I'm going to draw like a piecewise function here. Let's see. We're going to go that and that. I'm going to call that f of x. That work? So it's a really weird deal. I mean, it's not a continuous function. Let me tell you this. Some of the things that I do want to talk to you about today, and I've kind of got two things going on at once here. I want to talk about when is something differentiable, or in other words, when can we find the derivative, and I want to give you a whole bunch of shortcuts to find derivatives very, very quickly. Okay? So I'm trying to mesh two things here. And the other aspect with this derivative, and I'll keep coming back to it, is every time you find a derivative, what you are really doing is you are talking about slope of that curve at a specific point. Okay? So with that, from here to here, could you tell me the slope of that line?
Yes.
Yeah, what does it seem to be?
1.
1. So if I did tangent lines anywhere along those points, what would the slopes of the tangent lines be?
1.
1. They would be the same. So if I want to come back here and draw the derivative, I want to draw f prime. Okay, and remember that f prime is notation for derivative. And a lot of times let this be the guide of whether you want to call it f prime, y prime, ddx, or whatever. They called it f of x, so I'm probably going to work in f prime. Okay? So f prime, I'm hearing the slope of that is 1. Okay, well, at that point, there is no ability for me to have a point, and I am not differentiable where it is not continuous. So here's what this looks like. Open circle, straight line at 1, open circle. F prime does not exist at that discontinuous point. Does that work for you? Okay. The black line is going to be f prime. Right? Now, let's talk about the slope of f here. What are the slopes of the tangent lines there going to be? What is 0?
0.
So f prime is going to look like that. That work? Okay. I'm going to solid that in a little bit so that you can see. I might even just solid that in. Okay. And again, look at the connection. Okay. If I picked my x value as negative 1, 2, 3, 4, which is right there, the slope of that line at that point is 1, and the value of the derivative at that point is 1. Right here at negative 2, the slope at negative 2 of the function is 0. The value of the derivative at negative 2 is 0. And at any point in between there, really. Okay? How about from negative 1 to 1? What's our slope of that function? Negative 1. All right, so if I want to draw the derivative, it looks like this. Please note my open circles, because at those points I am not differentiable. Okay? And now from 1 to 4. Now the slope jumps to what? 2. Okay, cool. So from 1 to 4, my slopes are 2. And I'm going to note that my black line is f prime of x. Okay, and what I really, really want to tie into is this. The slope of that is represented by what the value of f prime is. Okay. Does that work? All right, let's talk about parent functions. absolute value of x. What do absolute values look like?
A V.
Perfect V's. Okay, so let's move on to something like this. Let's say, okay, again, I'm trying to get you to get a graphical connection before we just start rolling out equations. Okay, so now I'm going to do, and that's going to be f of x, which equals the absolute value of x. Okay? So let's sketch the derivative. The derivative is going to tell us about the slopes of tangent lines. So let's take this from negative infinity up to 0. What is the slope of every tangent line from negative infinity? And we start thinking tangent, 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 tangent. What slopes are we looking at? -1. Never changes, does it, until it hits 0. Okay, so let's go and we're going to look at our f prime is going to look like this. Now let's talk about this point right here. Right here where it changes directions. That's a dilemma. Is it? Is that really tangent though?
I don't know.
Remember what tangent allows you to do? Remember yesterday on Desmos when I was zooming in and it looked like that tangent line and the curve became the same line? Well, if I zoom in onto a tangent line at the point of the change of direction on the absolute value, you are not going to get the term that they would call local linearity. You're going to have a V and a line. In other words, no matter how you zoom in, that's what you're going to see. And you could keep getting closer and closer and closer, and they are not going to mesh. And that's why I need to tell you that the other place that derivatives don't exist, sharp turns. Anytime there is a sharp change of direction, you do not have a derivative being existing. So that means right here at this point, I'm going open circle. Because the derivative does not exist at 0. So there's two requirements of differentiability. Smooth and continuous, no sharp turns. And that's really the only two that we got to really be concerned with. I'm going to write that on here too for those that aren't here. But let's continue here. From 0 on to infinity, what will the slope of the tangent line be? 1. Okay. Open circle on to infinity. And that green line is f prime of x. But what does f prime of x equal? Let's get an equation. Well, hey, what's the equation of that line? What is it? -1. So this is a piecewise function where we're -1 when x is less than 0. Okay. When x is greater than 0, what's the equation of our line? 1. When x is larger than 0. And again, I reference you back to this dilemma. I don't know whether it's filled in top or bottom. There's definitely a jump, but there's no smoothness. And one of the things that they would say is that you have to have a right-hand and left-hand derivative that are the same. That's not really a big AP calculus thing, so I'm not going to jump into it a little bit. But what they're saying is, as you're approaching a point from the left and you approach it from the right, if they have essentially the same derivative, then you have a derivative at that point. And here there is a definite, hard change in direction. So it does not exist.
So you just can't get the derivative at 0.
Correct.
At other ones you can. Like 2.
At every other point you can. Yeah. So like if we said, hey, here x is 2. There's the value of x of 2. The slope of the tangent at 2 is 1. Okay, because it's at 2, right? You got that. Okay? And there's f prime, and there's an equation. Am I making some sense? Does this kind of work okay? Right? And what's weird is that people see that out of context, and that's like one of the hardest things for them to deal with. They're like, I don't know how to deal with that. Well, visually, you should now. All right? Think parent functions. And again, Why does AP Calculus want you to think about it graphically, numerically, and analytically? Because this stuff doesn't make sense if you only try to think about it one way. If you only try to do things analytically, you're losing 2/3 of the experience. Okay? But if you understand things visually and analytically, it starts locking together and making sense. Okay? So let me go under here and give you these two conditions. To be differentiable, and differentiable basically means for a derivative to exist. To be differentiable, you have to have two characteristics: continuous now. I think this kind of leads to what Hank was talking about too. No sharp terms. That means the derivative exists everywhere else. It just doesn't exist where the sharp turn is. Okay, so this would be, maybe a better way would be to say to be differentiable at a point. Okay, so to be differentiable at a specific point, you have to be continuous. You can't have sharp turns. Right? And I'll just note, f prime of 0 does not exist for f of x equal to absolute value of x, and then I'll draw that little point up there for the sharp turn. Okay? Good to go? Makes some sense. All right, let's expand on this a little bit, and let's try this picture. All right, so I'm going to put point A at 0, 1. I'm going to put point B up there a little bit above 4, a little bit between there, so we're going to put point B right about there. Point C right there. There's going to be D. I'm going to go with E right about there. We'll take F right about there. I might even throw a G out here. My curve that I'm working with is I'm going to connect these. There.
So do you need to see the graph to know if it's differentiable?
It helps.
At the sharp turns?
Uh-huh, yeah. Well, do you need to? No. If you do, you can see it right away because sharp turns jump at you. But what's really, what are the only two times where sharp turns kind of come at you? One you just saw. Absolute values, okay. So right away, if you're like, oh, find the derivative of an absolute value, you're in your head thinking, at one point, this thing's not existing, wherever there's a sharp turn. And we know that absolute values can be upside down or here, they can get squinched there, or they can get widened out. But no matter where that V turn is, you're having a sharp turn. The other place where they can happen, piecewise functions. Because you could go from an x squared graph to suddenly a y equals x graph, and they could make them join up, and they're still continuous, right? So it meets the continuity, but there is a definite change. There's not a smooth transition to there. And so at that point, it would also not be differentiable. Okay, so really that's the only time. Almost all straight up polynomial functions are going to be differentiable. They all are. Okay? Rational functions where they have a denominator, they're not going to be differentiable anywhere there's a whole or an asymptote. So that kind of gives you an idea of, yeah, that's why we talk about asymptotes, continuity, all of those things in pre-calculus. Because where those things happen, calculus doesn't work, it fails. Okay? Okay, so from here, I want to just maybe sketch myself a picture of f prime. Based on these points A, B, C, D, E. I didn't label F, did I, for some reason? Okay, so based on these points, I would like to sketch an f prime. So we are going to sketch f prime of x based on A, B, C, D, E, F, and G. Okay, we'll do it in yellow. All right? Don't necessarily start with A, B, A, because there's some points that are really good to start with, like C. And remember what the derivative is going to do. F prime gives us the values of the tangent line slopes at those locations. So here's C.
0.
Tangent line of 0. Okay? And so I might do this. I'm going to just give myself a little tangent line right there. It's got a slope of 0. That means that f prime has to pass through 0. Make sense? Where else is the derivative 0? F. Okay, so straight down from F, the derivative graph has to pass through 0. Okay. Okay, now let's look at, yeah, go.
So A and G, oh, that's not differentiable, right?
Correct, it's not really. So we'll have open circles on either end. Okay, but it will give us an idea about where to start from. Some other questions before I get actual details. Tell me about the slopes of the tangents from A to C.
Positive.
Positive, right? That means that the derivative graph from A to C is above the x-axis. That work? Tell me about the slopes of the tangents from C to F. Negative. The graph of the derivative is below the x-axis. A little bit of foreshadowing here. Can you now tell me if a function is increasing or decreasing based on the value of its derivative? If a derivative value is positive, the function is increasing. Right? And if the derivative value is negative, the function is decreasing. Okay? Foreshadowing, that's a bigger topic later. Okay? From F to G, what's true about the derivative? Positive. We've got positive tangent lines. Okay, so let's then do this. Let's take it at A. Give me an estimate, a numeric estimate or so for what you think the tangent line at A is. And if I were to draw that in, what's that? 3-ish. I heard 4-ish. Okay, it's steep, is it not? Okay. I'm not going to be able to be perfectly accurate here because I don't know the equation, but it's fairly steep and positive, and as it moves here, what's happening to them? They're decreasing, they're getting smaller, yet they're still positive, right? Okay, so I'm going to do something like this. I might say, all right, I'm going to go up, I'll put it somewhere up here about there, and I'm going to call that A prime. Where does B prime have to exist? Somewhere between here and here? Okay. But closer to what? It almost looks like it's 1. We'll do that. There's B prime. Here's the graph of the derivative so far as I see it. And it just checks. Are my slopes positive and is my derivative above the x-axis? Check. As I am getting closer to C, are my derivative values getting closer to 0? If I let this pattern continue, I think I see this happening. And honestly, if I did a better job of sketching this out, it's the green one, there is a point somewhere in here where, okay, we're starting to really accelerate our negative, and then we start flattening out again. See where I'm getting at? So here we're at 0, but then we start getting negative, 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 more negative, till right about there, then we start becoming less negative and turn around and hit towards 0. Which means probably right about there, oh, gotta be in yellow. The graph has to do that. Look at these. All right, we're negative, we're negative, we're negative. Right there, there's our maximum negative, which is right about there. Because the tangent line slope right about there is as steep as it's going to get, then it starts flattening out. And so that means it's going to start heading back to 0, which means E prime is somewheres right there. It is definitely negative, but it is on its way back to 0. We've talked about points of inflection, haven't we, of graphs?
Yeah.
Where the point of inflection exists is where the minimum of the derivative exists, and there will be that connection. Foreshadowing. Yeah.
Isn't it kind of like make like an S curve as it goes like past like the axis because it's getting like steeper, you know? So
Yeah.
it has to drop faster. So would it be shaped?
Like, are you thinking something like?
Yes.
Okay. Well, but what you said is actually what it's doing. It's steep, 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 but it's actually slowing down. So it's not getting faster, it's getting, and the rate that okay.
Yeah, but as it comes down below the line, wouldn't it kind of? Because if the slope was -1, the point would be at -1. But then if you go from like D to E, and then it gets to like 3, so then you go down to 3. That would make a curve.
Oh, I see what you're saying, is that I'm probably not going down far enough, but I think in a minute you're gonna disagree with yourself.
Okay.
I think you're gonna say, wait, I see a connection here. But I do agree with something that you're saying. Because my min slope there wasn't even at 1 yet. These slopes, and I think I'm seeing this happen, I think I'm too pronounced there. I think I should be almost straighter. Because I think this needs to dig deeper, because these slopes right here are probably about -3.
Yeah.
Okay, and so I think I see what you're saying. You're saying, does it need to, because of how I drew it, and then does it need to do something like that?
Yes.
I'm with you now, and I think what I can alleviate that with is if I drew it a little bit better. Okay, I want to use that. And I think what I would do better with is if it did this. Maybe somewhere's in there. And I think my G prime is too tall or too high. Okay, I think this is fairly inaccurate. I mean, but really, in reality, here's what an AP multiple choice question on this kind of topic, and yeah, they would have them. They would give you this curve, and then you would have four options, and they would say, which of these graphs could be the derivative graph? And really, what you would want to do is you would say, okay, identify the zeros, and then look at your 4 graphs. Which ones have zeros in the proper location? 2 of them won't. You'll be able to eliminate 2 of them. Then you're going to say, okay, I need to be below the x-axis from there to there. Which one is and which one isn't? All right, so that their accuracy about are we at the exact value? They don't even put an XY grid on it. They just give you an XY axis and don't tell you where they're really at. So really, at this point, I'm just trying to get you to see characteristics, because that's really all they want you to see. Okay, the positive slopes, the derivatives above. We're getting closer to 0. It's decreasing. Okay? And I do have a matching game that we can play where there's cards of the graph and the derivative and the equation of the derivative. And we push it out there and you walk around and match with each other. So I have that, but today is not that day. Okay. Okay. Let's, yeah. Oh, I did. And I believe there needs to be. And these are the inconsistencies too with AP calculus. If they will never differentiate two graphs by open circles versus closed circles. So sometimes they'll close them, and it's a frustrating thing to me. And some books will allow you to do it, and they'll say, well, the left-hand derivative is this, so we'll go ahead and allow it. And so AP Calculus doesn't split hairs on like that multiple choice question. You wouldn't have this graph and then the same graph with them filled in and have to make the decision. They'll either fill them in, and so like, or they'll leave them open. And some people, when you start seeing sample questions, you'll be like, why is that one filled in and this one not? And I'm like, because some people disagree about calculus. It's honest. Like I say, I don't know if I haven't told this class because you guys are brand new. They ran into a question a couple years ago that was such a vague type of thing, and there was so much disagreement out there among people, they threw it out. They got into the grading, and they went, well, it could be this, and it could have been this, they just chucked it. Said, well, we can't ever ask that again because there's too much gray area. So, and you'll see that as we get into this stuff. Okay. So let's get into some shortcut rules. Let's use our graphs, and I did that for a reason, because the shortcut graphs and the shortcuts and the graphs I can tie together. Okay. I'm naturally going to start this with the graph. I'm going to start you with y equals 2. We can graph that, I think. Oh, Mason Russell taught me something cool. I just got to remember it. He told me that there's a way for me to just insert an XY axis.
It was on the thing. Yeah, it's on the.
Is it really?
Yeah, we showed it the
Oh,
one.
boom, right there. Absolutely cool, okay. But there's y equals 2. Okay? What are the slopes of the tangent line? All right, so we have some visual understanding of what tangent lines look like.
0.
So what are they? 0, right? Okay, so if y is 2, y prime equals 0. And I'm gonna jump between notations here a bunch in this little thing, just so that you can see me using them interchangeably. So here I'm in the y and y prime notation. Okay? Now, here's something that's cool to me. What if I graph y equals 3?
Still 0.
Still 0. How about y equals -4? Still 0. The derivative of any constant is 0. Which means, and I'll do a couple of things here. So if I did d dx 5, the derivative with respect to x of 5, 0. If
Teachers, pardon the interruption. You would keep all students in your classroom at this time. We're going to have a K-9 inspection. So if you can keep all students in your class and continue to teach, keep all students in your class. We'll let you know when they're available to move again. Please keep all students in your class.
See, things you should never do when they announce a drug dog is like, show some in your bag. I got
Get
lucky.
your drugs out. One time the drug dog did find it. But at the,
Really?
yeah, and then Mr. Mace was like, so curious, it's such a locker. And I was like, I just haven't been out.
Funny. Yeah.
Maddie brought her backpack in here to be basically.
Oh, we'll have to let the dog in then.
Only day she's ever brought it in.
Only day she ever brought it in?
Yeah.
Did you know this was happening?
Yes.
Really? It's on video for you just saying that, by the way.
Her mom's a board member. She knows.
She
Support
knows.
it.
So you knew?
So is yours.
Yeah, duh.
She didn't tell me anything.
Okay, so if f of x is 7, f prime of x is 0. the derivative. So here's rule 1. Derivative with respect to x of a constant is 0 for c equal to a constant. And there's the visual evidence that breaks it up. Okay? And the thing that's awesome about this, don't write this yet. If you remember our limit rules, how I could break and do limits a piece at a time on a function? And we said, hey, we can do the limit of this, plus the limit of this, plus the limit of this, and we can do them as 3 separates. You know what that lets us do is it lets us do the derivative of individual pieces one at a time. It means that if I had this, f of x is 6x to the 5th plus 4x to the 4th minus 3x cubed plus 2x minus 8. That limit rule that lets us break this up means that you can take the derivative of each of these separately. And I bring that up because there's an 8 right there. 8's a constant. I can do the derivative of the constant separately. What will that turn into?
0.
And you see the formation of a shortcut. I didn't have to go through f of x plus h minus f of x all over h with the limit as h goes to 0 because visually I'm getting to see this. Okay? All right. Next rule. Am I good with that? Able to move on? Okay. All right. Let's try the Mason-Russick xy axis. How do I get it to appear? Oh, yeah. Okay. The line that I now want is this. Y equals 2x. So that would be y equals 2x. Yeah? Visually, because now we've set ourselves up and we understand what derivatives look like visually, and we understand that derivatives reference us slopes, and y equals 2x, and we can now, okay, what's the slope of any tangent line to that equation? 2, right? Y equals 2. Okay, so that means that I can come along here and say, okay, I'm going to draw the line. Oh, that even came up in green. That came up in yellow. So y prime is 2. And now you start seeing some coolness to this. Wow, if I just decrease the value of the variable by 1 power,